For the first time in history, a spacecraft has dared to enter the atmosphere of the Sun. The Parker Solar Probe's achievement will always be remembered, because no metal or the toughest material in the world can normally survive such extreme heat. So the question arises, why doesn't the Parker Solar Probe melt, even in temperatures of millions of degrees? How is it functioning perfectly in such conditions? Back in the early 1900s, scientists noticed something strange while researching the Sun. Using spectrographs from Earth, they studied the wavelengths and colors of the light coming from the Sun, which directly reveal temperature. But what they discovered created a mystery that has never been fully solved. They observed that the surface of the Sun has a temperature of about 5,500 degrees Celsius, but its outer atmospheric layer, the corona, is mysteriously hotter, reaching over 500,000 degrees Celsius. That's at least 100 times hotter than the surface itself. It's like moving away from a fire and somehow feeling even more heat. This bizarre phenomenon has puzzled scientists for more than 100 years. Normally, the corona is hidden in the Sun's brightness and can only be observed during a solar eclipse or with special instruments like a coronagraph. After NASA was established in 1958, several space missions were launched, but to truly understand this strange phenomenon, scientists needed a probe that could actually travel into the Sun's corona and study it up close. They wanted to measure the Sun's rays in a region where temperatures soar to 500,000 degrees Celsius. But the challenge was enormous, because even imagining such heat was difficult. For perspective, iron melts at just 1,500 degrees Celsius, and tungsten, the toughest metal on Earth, melts at 3,422 degrees Celsius. Both would instantly melt on the Sun's surface itself. Now imagine what would happen in the corona, where temperatures are hundreds of times higher. But that wasn't the only problem. Reaching the Sun itself is extremely difficult. To understand why, first look at how spacecraft normally travel. If a satellite needs to return from Earth's orbit, its speed must be reduced so Earth's gravity can pull it back. If it needs to go to another planet, its speed must be increased to escape Earth's orbit. For example, to send a spacecraft to Mars, rockets first place it in Earth's orbit, then at the right time, angle, and speed, it is directed outward toward Mars. Leaving Earth's orbit requires enormous amounts of energy. Rockets push the spacecraft into orbit, but to go further, onboard thrusters must be used. Since Mars is closer to the Sun than Earth, the launch angle doesn't need to be too large. But the distance between Earth and the Sun is about 150 million kilometers, and reaching the Sun's orbit requires an even steeper angle and far more energy than any rocket ever built. So NASA's experts decided to use Venus to help. By flying Parker Solar Probe close to Venus, its gravity could be used to adjust the probe speed and trajectory. But Venus is small, with weaker gravity, so one flyby wasn't enough. Parker Solar Probe had to orbit Venus 24 times before it could finally reach its closest approach to the Sun. On August 12, 2018, the Parker Solar Probe was launched from Cape Canaveral Air Force Station. NASA planned an 8-year mission in which Venus would assist the probe 24 times. Each orbit would give about 37 hours of opportunity to study the Sun, resulting in around 900 hours of research across the mission. On April 28, 2021, NASA confirmed that Parker Solar Probe had successfully entered the Sun's corona. It proved that the corona is indeed hundreds of times hotter than the surface, but the reason why remains a mystery. What hidden force makes the corona so incredibly hot? Research is still ongoing. Now let's return to the main question. Why doesn't Parker Solar Probe melt in such intense heat? The side of the probe facing the Sun is protected by a heat shield made of carbon foam. This isn't ordinary foam. It was specially engineered by the Ultramet company to absorb and withstand extreme solar heat. The foam itself is 97% empty space, which makes it even more effective. On top of that, layers of carbon-carbon composite made from graphite and resin were added, then superheated to turn them into pure carbon. Carbon has excellent heat conductivity, which makes the shield even stronger. Finally, the sun-facing side of the shield was coated with white ceramic paint to reflect most of the sunlight before it could penetrate. The rest of the probe is designed to stay hidden in the shield's shadow at all times. Even with this protection, Parker Solar Probe can only withstand up to 2,500 degrees Celsius. But since the corona's temperature reaches 500,000 degrees Celsius, how does it survive? The answer lies in the laws of thermodynamics. Heat needs a medium to transfer. On Earth, particles in the air carry heat, which is why even at night the air can feel hot after a scorching day. But in the Sun's corona, particles are so sparse that heat transfer is minimal. That's why the probe can survive. It's like dipping your hand into boiling water. You'd burn instantly because the water molecules touch your skin. But if you quickly place your hand in a 300 degrees Celsius oven, you might not even notice the heat, because there's no medium directly transferring it. According to experts, the heat shield facing the sun experiences about 1,200 degrees Celsius, while the rear side of the probe, in shadow, remains below freezing. With so few particles around to transfer heat, Parker Solar Probe can study the sun's corona up close without melting. We hope you enjoyed this video. Don't forget to like and share it, and thank you for your wonderful comments. See you again in the next amazing video.